Megan Lang is a postdoctoral scholar with the Clean Climate Action Initiative from JPL, currently based at the University of California, Santa Barbara. Megan received her doctorate in agricultural and resource economics from UC Berkeley and has previously researched rural electrification and women-owned enterprises. Megan, let me pin you, and the floor is yours.
Great, thank you, Fernando. So this paper is just called Cherry Picking, and it's joint with Wenfeng Chu, who unfortunately can't be here today. And this is still a work in progress, so I'm hoping to stop talking within at least 20 minutes and leave a little bit of time for your comments and discussion at the end, because we would very much appreciate all of those. So when we're motivating this paper, I think it's important to point out that we are going to explicitly be thinking about this kind of invisible or imaginary person who we're calling the unscrupulous researcher. And so it's important to be clear here that we're going to think about unethical behavior very explicitly.
Megan, I'm sorry to interrupt you. I can see your face as the primary image.
Okay.
I don't know if that's because I did something wrong with the pinning.
Let me just stop sharing and try sharing again.
Sorry about that.
No, thank you for telling me.
Now I can see the slides. Okay. Yeah.
Awesome. Great. Thanks, Fernando.
Yeah.
All right. So the current norm, at least in economics, given the institutions that we've set up, is we're trying to limit researcher degrees of freedom as a way to prevent the positive selection of statistically significant results. So we do that through a number of mechanisms. We have pre-analysis plans. We're increasingly sharing our data and our code. We're doing things like multiple inference corrections, and these are all great. But it's important to point out that all of these institutions provide relatively little prevention or detection of fraud. And we're not the only people to point this out. Multiple other scholars have already pointed this out. And so the starting point for this paper is just going to say that we know that a lot of time and sometimes money goes into conducting research, and there's a continued perception that publishing null results is difficult. So our starting point is just that researchers face incentives to manipulate results. And so we're going to be thinking about this researcher who has kind of fallen prey to this temptation for manipulation. So to provide an incomplete summary of p-hacking, we've already touched on this, but p-hacking can happen in many ways, but we think that there are some ways that are already kind of addressed by the institutions that we have. So if you're going around and searching for different model specifications, that's something that hopefully robustness checks end up uncovering through the publication process. If you're trying to select outcome variables that have positive results, that's something that we're trying to address with pre-analysis plans and multiple inference corrections. So we're, in this paper, going to be thinking specifically about data manipulation, and within the kind of large set of things that could fall under data manipulation, we're going to think about selectively dropping observations. Now, it's important to note that in theory, pre-analysis plans are supposed to prevent this, but in practice, this isn't something that's very feasible to enforce. And in particular, what we'll mention later is that it's going to be straightforward for an unscrupulous researcher to game this aspect of a pre-analysis plan. All right, so what we're going to do in this paper is introduce an undetectable algorithm that cherry picks observations to produce artificially high average treatment effects. So to be a little bit more specific, when we say that it's undetectable, what we mean is that the cherry-picked data set that our algorithm is going to produce is statistically indistinguishable from a random subset of the data. And when we say artificial, what we really do mean is that the average treatment effects that we identify are due to random noise. And it's important to point this out kind of upfront. Our algorithm is not a way to do something cool like uncover unobserved heterogeneity. A lot of applied people like to think that that's what our algorithm is doing. So I just would like to preempt that question a little bit. And then when we say that these average treatment effects are high, what we find is that even with large subsets of data, our average treatment effects are an order of magnitude higher than the true, or what maybe we should call the accurate treatment effect, which is the treatment effect estimated on the full data set. All right, so I'd first like to walk you through a simulated example, and then I'll walk you through an example with real world data. But the simulated example is, of course, going to be nice because we're going to define a data generating process that behaves in a way that's very easy to understand. So here you can see our data generating process. We have y, which is some outcome of interest. It's going to be a function of x1 and x2, which are covariates that could be correlated with each other as well as with the epsilon term. And then d here is a randomly assigned treatment. And as you can see in the true data generating process, this randomly assigned treatment is not going to have any effect on the outcome y. So in the simulation, all we're going to do is generate 2,000 observations where we're drawing x1, x2, and epsilon from a multivariate normal distribution. We'll randomly assign 30% to be treated. Obviously, we could choose whatever we want for the random assignment. And the first thing we're just going to check is that everything looks the way it's supposed to. So I'll just briefly show you that here on the left, you'll see that the control and treatment groups are balanced on the covariates, as you would expect. And on the right, you can see that regardless of the specification that we use, we're not going to find an average treatment effect that is significant at the 5% level. So hopefully all of this is what you were expecting given the data generating process so far. So next, what we're going to do is use our cherry picking algorithm. And the way that this algorithm works is that we're going to calculate a score for each observation, and then we're going to cherry pick based on those scores. So the first step is just initialize the score for each observation, which will index with I to be 0. And we're going to define tau naught as the average treatment effect that you get when you use all observations. So after that, you're just going to iterate through. So if you index each round with k, you'll randomly draw a sample called S sub k from the original data containing n sub k observations without replacement. So for us, we're going to draw subsets of 1,000 observations without replacement. And then we're going to estimate the average treatment effect just on S sub k and denote that as tau sub k. So once we do that, we'll update the score for each observation that ended up in the sample sk by just adding the difference between tau k and tau naught to its existing score. And the thing that's really important to note here is that tau k minus tau naught is just the bias that comes from random sampling. And so given that in the example that I'm showing you right now, we know the data generating process. We know that that variation is just spurious and it's not actually the variation that we want to be using to identify a treatment effect. So basically, you're just going to go through that process many times. We're going to do this 500 times in our example. And then once we have this set of scores, we're just going to cherry pick based on the final scores. So for instance, we can choose the 75% of observations that have the highest scores. All right, so when we do this, I'm just going to show you a comparison of the full data set versus the cherry-picked subsample. And the first thing that I'll show you is that the subsample is undetectable. So here you can see that the cherry-picked sample is still balanced on treatment and control. And if you compare the values of all of the variables between the full data set and the cherry-picked data set, none of them are statistically significantly different. So that's the first result. The second result is that, as you would expect, our cherry-picked subset ends up having significantly higher treatment effects. And so in columns 3 and 4, I'm showing you the results for our cherry-picked subset versus columns 1 and 2, where we estimated average treatment effects on the full data set. So as you can see, these are much larger treatment effects than kind of the accurate ones that we estimate on the full data set. And so this figure basically considers what happens when you choose different sizes of subsets. So again, once you have the scores, you can choose a subset which is as small or as large as you would like. And so the red line is showing the average treatment effect that we get when we choose increasingly large or small subsets of data. And then we're showing you a 99% confidence interval around that average treatment effect. And so the important thing to note here is you could drop as little as 5% of the data and still come up with a treatment effect that is statistically significant at the 1% level. All right, so what I showed you so far is that at least in this simulation, we can pick a large subset of data that's indistinguishable from a random subset and that yields large and statistically significant average treatment effects on some outcome Y. In the paper, we show that this extends to multiple outcomes. I'll hold on that for now because I'll also show you that in the real world data. And so then I'll kind of go into the more applied part of this paper where we see what this looks like in kind of a real world situation. So what we're doing in the second part of the paper is just take a well-known kind of null effects paper, which is this Banerjee et al. 2015 study, which is looking at the effects of Spandana. And that's just going to be a microcredit program in Hyderabad, India. So in the paper, what we're going to do is use our algorithm to cherry pick observations to get a positive average treatment effect on consumption expenditures. And it's important to note here that, of course, this paper is going to look at multiple outcomes. Consumption expenditures just happens to be one where they have null effects in the original paper. So that's what we're going to be looking at. And then again, I'll kind of get back to this question of multiple outcomes a little bit later. Now, once we do that, we're going to test and see if our selected subset differs from the full sample. So again, is this undetectable? And then I'm going to go through a number of what we're calling natural deterrents that we think might preclude cherry picking. Okay, so this is what I'll show you first. When we cherry pick in the first column, you'll just see what happens when we reproduce the result that's in the original paper. So you can see there's a treatment effect of about 10, which is not statistically significant. You can see when we have a 75% cherry picked subsample, we get something that's over 30 times larger than that. And even with a 95% subsample, we're getting something that's 15 times larger. So our cherry picking in this real world data set still yields large and significant average treatment effects. We can also show that if we test the distributions between the covariates in our cherry picked subsamples and the original data set, we really can't reject that they are the same. And so again, it seems like this is undetectable. So now I'm going to go through kind of a bunch of natural deterrents to cherry picking. And so all of these are motivated by the thought that even if someone was using this algorithm, they can only cherry pick based on the specification that they're using in the algorithm, right? So you kind of have to choose the specification and use that to assign scores. And so it seems like that maybe is, from the perspective of the unscrupulous researcher, maybe that's a fatal flaw in this algorithm, and that could actually give rise to natural deterrents, and maybe this isn't something that we need to worry about. So I'm going to kind of think through a number of things here that could happen. One thing that you might think is helpful is just that we know that a lot of RCTs follow more complex sampling strategies. So maybe you have stratified your sample, maybe you have done some sort of cluster randomization. And what that means is that if you were to cherry pick data, you would need to make sure that the data set that results still reflects whatever type of stratified sampling or cluster randomization that you pre-registered. So in the context of this paper, they don't do explicit stratification, but we can basically just see which neighborhoods are represented in their data set, and we can restrict our cherry pick subsample to say it has to have the same proportion coming from each neighborhood as the original data set does. So in this case, we're not changing anything about the algorithm itself. This is just after we've assigned all of the scores, we're going to look and see what happens when we impose the additional restriction that the distribution of observations between neighborhoods has to look the same. And so this is showing the results in columns 3 and 5 is what I've already showed you. And then columns 4 and 6 is showing what happens when we impose the additional restriction. And what you can see is that it's true that imposing that additional restriction erodes kind of how well this algorithm is performing, quote unquote, but not nearly as much as the overall gain that you get from using the algorithm in the first place. So it doesn't look like this more complex sampling is providing a very strong natural deterrent. The next things that we're thinking about are just a number of things that you could kind of imagine referees asking for during the publication process. So one thought that we had is that the authors kind of provide weights that they recommend using with their replication files. So we're asking, what if you use different weights, or in our case, we just decide to use no weights. So in columns 1 and 2, you can see how much that changes the results when you are using the overall sample. You again see that that doesn't change the results very much when you're using our cherry picked sample. The other thing that we could do is just look at different combinations of control variables. So in this case, what we're doing is taking directly Broderick and co-authors 2020 paper and the associated very user-friendly data code, where you basically just look at every possible combination of covariates that you could be including in a regression. And the thing that's important to note here is that there are about like 6 covariates that we actually use in the algorithm. We're going to go further than that and include in this kind of test all of the possible covariates that we could be using from the data set. So this is going to include some covariates that we didn't use in the algorithm to begin with. So this is what their very nice data code outputs. On the top left panel, you see just the distribution of t-statistics that you get from using every possible combination of covariates. And as you can see, all of these are going to remain highly statistically significant. On the upper right, you can see the effect curve. So this again is what effect size are you getting using every possible combination of covariates. And again, you can see that this entire distribution is more than 10 times higher than the effect with the full data set. So again, this looks remarkably robust to including any different combination of covariates that you might be asked to show by a referee. Similarly, we can look at different functional forms. We can just do like an inverse hyperbolic sign transformation. We still end up with a significant treatment effect. The one place where we have a little bit of hope is a very recent measure of robustness from Broderick, Giordano, and Meager. So for those who aren't familiar with this recent paper, basically the paper asks how much data would you need to remove to change either the significance level of a result, the sign of a result, or both. And so when we look at our 95% cherry-picked subsample, we see that our results are not very robust. Dropping just 1.1% of the data changes the significance level of the result. Obviously, that's going to be much higher for the 75% cherry-picked subsample, which is dropping about 9% of the data. Now, we discussed this more in the paper. Basically, we think it's actually fairly intuitive that this measure of robustness is going to be able to highlight a little bit the shortcomings of the algorithm, because they're actually doing something very similar to what we're doing, but because they aren't thinking about kind of cheating per se, they're not going to restrict the data set that results from dropping the most influential observations to be undetectable. Right, and so basically they're doing some sort of maximization which is less constrained than what we're doing. So this is, we think, a little bit of a positive result. It's potentially one natural deterrent to this type of cheating. But we think that there's an important caveat here, which is that the authors themselves show that there are multiple studies that exist that are not robust to dropping 1%, or in some cases even less of the data. And we're not trying to say that we think that those studies manipulated data or anything like that. We're just pointing out that our results are also not robust to their measure. And so I think here it's kind of a situation where, you know, this would be a necessary but not sufficient condition for kind of wondering whether some manipulation had happened ex post. Okay, and then the last thing I'll just talk about is multiple outcomes. So this, to me, as a development economist, seemed like the most promising avenue to think through, you know, reasons why you wouldn't want to do this in practice. So basically, if you have multiple outcomes, but you're cherry picking based only on a single outcome, then it's possible that you would basically just get results that didn't make sense. So basically, if you're cherry picking for instance, a really high average treatment effect on consumption, but then you can't show the same positive effect on something like micro enterprise profits or things like that, you just end up with a paper that doesn't really make sense, and that wouldn't be easy to publish. So what we're going to do is use the same cherry-picked data set. So again, the data set that we cherry-picked based on consumption expenditures. And then we're going to re-estimate treatment effects on a range of business outcomes that they estimate treatment effects for in the original paper. So this table is just summarizing all of those. And so here you can see the results where we just reproduce what they have in the original paper, and then the results using our 95% cherry-picked data set. And so what you can see here is that certainly it's not always true that our cherry-picked data set ends up with positive treatment effects in every single category, but there are quite a few where we end up with larger treatment effects that become statistically significant. And the thing to note here is that, of course, this is happening because all of these measures are correlated with consumption expenditures, but we were surprised to see that actually those correlations are relatively low, even for some measures where we end up finding significance in our cherry-picked subset. And so this was, I think, for me, fairly disappointing. I thought that this would kind of save us a little bit, and it really does not seem like that's what we're seeing. All right, so with that, I'll just summarize quickly. Our cherry picking algorithm is selecting subsets of data undetectably that yield spuriously large and significant treatment effects. It looks like our results hold in simulations as well as using real world data. And so far as we can tell, there seem to be few natural deterrents to this type of behavior. So what we conclude with in the paper are thoughts about how to prevent this type of cherry picking from posing a temptation. And what we originally proposed in the paper is a system of third-party reporting. And so basically this just comes from the very simple observation that if you even just knew the number of non-missing observations for each variable in a data set, that would be sufficient to kind of enforcing this norm that we need to justify any data exclusions that we make in our analysis. Of course, the challenge with that is that you have to have a credible kind of third party who's doing that. So we kind of propose potentially survey firms to act as third parties. We're open to other thoughts about like how to make sure that there is a credible third party who isn't necessarily under the influence of the PI or of the researcher as well. Something that hasn't made it into the paper yet, but that we would love to continue hearing. We've heard from a lot of people since we posted the working paper who have other ideas. And so there's a recent paper out about incentive compatible critical values, which in some sense doesn't try to solve this problem at all, but instead just uses critical values that assume that people are tempted to p-hack and that they are p-hacking, but kind of accounts for it after the fact by imposing larger critical values. We've also had people reach out and ask about, fewer incentives around publication, more around long-term reproducibility, and of course, kind of those bigger field-wide changes are always things that can help as well. But again, we're open to other thoughts about this, as well as the paper in general. So I'll pause there, and yeah, I think Joel raised his hand, and I also have things in the chat. Yeah.
I know we don't have a lot of time, but one thought that came to mind was if you could use the score itself in the cherry-picked data set as a statistic. So like I would guess that the distribution of scores in the cherry-picked data set would be shifted to the right compared to like the original data set. And like if you could use that distributional difference as a way of testing for cherry-picked data sets.
Oh, interesting. But so basically like does the distribution of cherry-picked scores just look different?
Right, like
recompute
the score in the cherry-picked data set of all the observations and then see if that distribution looks different from in like a non-cherry-picked data set.
That's great. Yeah, we can do that. Thanks. In the chat, do I need to see? Okay, great.
I was also wondering if there's like this cherry picking procedure is also like if somebody were to apply it, it would be so like direct, like nefarious purposes, right? But if there's if there's any sort of like real life correlate of like something analogous to p-hacking where like it could be more unconscious, like you're sending the array to rerun the regressions and you get like an imperfect version of this algorithm.
Yeah, we have thought about that a little bit. We think that like in practice, it's unlikely that this ends up happening by accident. So yeah, we are kind of focused on people who are doing this explicitly for like unethical reasons. Yeah, certainly it can, I think it could happen indirectly, but I think that the effects of just like somewhat innocently going back and trying to run regressions on different subsets and things like that, it's unlikely that you would see the same magnitude in terms of how much your average treatment effects are changing.
And if the focus is on like scientific fraud, basically maybe it could be a good motivation to say, well, in for example, in psychology, there's a better grasp of scientific fraud because like the way they do their experiments, it's a little bit more standardized. So there is a closer measurement of fraud in economics or in field data or in less standardized type of studies. It could be harder to measure fraud. So this could be a contribution to that space. Annabelle raises hand.
Yeah, just quickly. Sorry, I missed part of the talk, but I'll listen on YouTube later on. I think actually p-hacking happens quite a lot by accident, just because it takes so much time to actually publish a paper. It's going to take years. You're going to start a data set. You're going to stop working on it, coming back to it. And I think you're kind of p-hacking your way, but it's through so many steps and so many months and so many mergings of data set that you don't even realize you're kind of doing it. So I don't know, you can kind of reproduce this in the way that you're building this kind of new data set that is kind of p-hack. But to me, at least, studying p-hacking for years and years, I think there's a process that is kind of happening that people are p-hacking, but are not sort of aware that they're actually p-hacking. I don't know if that makes sense.
Mm-hmm. Yeah, we can also do more work around, like trying to think through how much this could happen by accident through like dropping observations that in some sense you might think were justifiable to drop. I know that the paper with the other measure of robustness from Rachel Meager and co-authors does a little bit of that, and they can actually show that like in their case, the most influential observations are not necessarily what you might expect. Like they're not outliers, they're not things that like you would naturally think about dropping from your data set. But yeah, we can do more on that. Yeah,
or just, usually sometimes people p-hack, but it's not their fault. They're just using the data sets and what other people have done in the field. Right. You just kind of reproduce that, and I'm dropping like this type of people or whatever, and you end up p-hacking, but it's just because you're following the literature and there's this first person. I see p-hacking as something incredibly complex. That happens through a lot of iterations, a lot of things going on with the referees who are actually increasing p-hacking, and then going to another project using the same data set, somebody else. Like to me, p-hacking is insanely complicated actually to model. I mean, I think it's super important what you're doing and so on, but I think it also kind of makes me think of like the different processes that you can arise to exactly what you're showing.
Yeah,